now we're going to get into more details about the formation of ionic bonds. So, as we said before, ionic bonding occurs when you have the transfer of electrons from one atom, a metal, to another atom, which would be the nonmetal. And when that happens, the resulting ions will have a noble gas configuration. But you need to realize that they do not become noble gases. And the reason why is because it's not the same element as a noble gas, because the number of protons will be different for the ion compared to the noble gas element. So the resulting ions that are formed as a result of the transfer of electrons will end up being very strongly attracted to each other, and that is called an ion pair, basically a unit where the sodium or whatever the metal ion is attracted to the negatively charged ion, which is the anion. All right? And this strong force of attraction is what we refer to as the ionic bond between the cations and the anions. All right? Now, what will result from this is that the ions, if you think of it in terms of billions upon billions of particles, what they will do is assemble themselves into a very highly ordered arrangement, and we call this arrangement an ionic crystals. And to show you that in the case of sodium chloride, this is basically what it looks like here. Now, what this is showing you here is the actual reaction. If you put a small piece of sodium in this flask, which contains chlorine gas, you're going to get a violent explosive reaction generating a lot of heat, a lot of light. All right? So that's what happens. That's why you see this has a very bright yellow color. That's a light being produced as well as heat. If you were to touch the outside of this, it will feel very hot. So this is what's happening here. If you look at the particles themselves, the sodium atoms will give up its valence electrons to the valence shell of the chlorine atoms, and the result will be the formation of the sodium chloride. And this is what the crystal structure looks like. As you can see, it is basically a very ordered system, a very ordered arrangement that goes on and on and on throughout the whole growth structure of the sodium chloride. All right, and in this particular representation, the purple spheres represents the sodium ion, and the green spheres represents the chloride ion. All right, and what you're going to find, if you look at this structure in more detail, you'll see that there are several what we call repeat units, which we'll take a look at in a later chapter. But basically, what you'll find is that you can actually get to what is known as the unit cell, which is the smallest unit that is repeated throughout the whole structure. And that unit cell will have a specific arrangement, right? And the arrangement is actually dependent on the relative sizes of the ions, all right? So sodium chloride will have one particular arrangement for the unit cell, and another ionic compound will have another different arrangement, all right? So that's basically what happens in the formation of ionic compounds. Now, let's look at how Lewis symbols help us to represent what is taking place in ionic bonding, all right? First thing I want to say here is that we can use Lewis symbol to successfully represent ionic bonding between nonmetals and metals. And the type of metals we're talking about are the S block elements, and there are some P block elements, and very few of the D block elements. So there are very few instances where transition elements can be used successfully, or we can use Lewis symbols successfully to represent what is happening in the case of transition metals. Okay, so basically, if we're going to use the example of sodium chloride, this is the Lewis symbol for sodium, this is the Lewis symbol for the chlorine atom, and the sodium has one valence electron, which will be transferred to the chlorine atom, and you're going to end up with the chlorine now ending up with 8 electrons on its outer shell with a negative charge, and the sodium will have 8 electrons. Now, those 8 electrons would be the inner core electrons, not the valence electron that was lost here. So they're not shown here, right? Remember, the Lewis symbols only shows the valence electrons. So that's why you don't see the 8 electrons in the sodium ion explicitly shown here, right? So this is what we call the ion pair, the sodium and the chloride ion together forming the ion pair. So that's a simple example. Let's look at a more complex example. So the question is asking here in this example for the, okay, what's going on with this here? Let me do this here. Okay, whoops. Okay, so this example says, right, use those symbols to show the formation of the ionic bond between the magnesium and the nitrogen atoms, right? Now, the question is asking also, what are the name and formula for the compound that results? Okay, so in the case of magnesium, magnesium has two valence electrons, right? So basically, magnesium will lose two of those electrons to any nonmetal it reacts with. Now, in the case of nitrogen, let me erase this here. In the case of nitrogen, which is in group 5, okay, what's going on with this here? Nitrogen has 5 valence electrons, so I'm going to represent that here. 1, 2, 3, 4, 5. All right? So that's the nitrogen atom. So in the case of nitrogen, because it has 5 electrons, then the nitrogen atom will gain 3 more electrons in order to get a complete octet. So here we have a situation where the magnesium atom needs to lose 2 electrons and the nitrogen needs to gain 3 electrons. So the question is, how can that be achieved? Well, what that means therefore is that we need more atoms of nitrogen and magnesium. Now in the case of magnesium, you're going to need 3 atoms of magnesium, each having 2 valence electrons, and we're going to need 2 atoms of nitrogen, each having 5 valence electrons. And what's going to happen is the electron transference from the magnesium to the nitrogen atom. So this electron, for example, can be transferred to this nitrogen atom. This electron can be transferred to the same atom, and then this electron can be transferred to that same atom, right? And then this electron can be transferred to this atom here, and then the final 2 electrons here will be transferred to the same nitrogen atom here. All right? So what would be the result of that? The result of that is that you're going to end up with 3 magnesium 2+ ions, and you're going to end up with 3 nitrogen atoms, or I should say nitride ions, that will gain, in each case, that will now have an octet, and each of them will carry a -3 charge, all right? So to answer the next question, what are the name and the formula of the compounds that results? Well, the formula is Mg3N2, and the name of this compound is magnesium nitride. And that's basically how that is done. All right? Okay. So let's talk about energy changes in ionic compound formation. So what is being shown here? Let me go back to my pointer. Okay, so what is being shown here is the energy changes that takes place when sodium loses an electron. In other words, the first ionization energy and electron affinity for chlorine. In other words, the energy changes that takes place when the electron is added to the chlorine gaseous atom to form the chloride ion, right? Now, based on these 2 numbers here, if you were to add this equation to this equation, you'll see that the resulting delta H for that reaction is relatively small, right? So it doesn't appear that the formation of sodium chloride from its elements would be energetically favored. However, there are other things that you have to take into account, one of which would be the enthalpy of formation of the ionic compound. And what you'll find is that that enthalpy is actually more important than either the first ionization energy or the electron affinity. All right? So what we're going to look at is actually an overall enthalpy picture that can be shown to show you the energy changes that will take place. And we call that a Born-Haber cycle. All right? So in the case of sodium chloride, this is what the Born-Haber cycle looks like. All right? So let me try to explain what's happening here. Well, let me just say this. Firstly, before I say that. So what we're starting off here with is sodium solid and chlorine gas, right? And you'll notice that it's 1 mole of sodium solid reacting with half a mole of chlorine gas, because we're looking at the formation of 1 mole of sodium chloride. So we're starting off with this, right, the sodium and the chlorine, and we're ending up with the sodium chloride solid. The enthalpy of formation for that is given right here. Delta HF standard is equal to minus 411 kilojoules, all right? Now, the key thing you need to recognize is that the reaction that is taking place here will not take place in just one step. It's a combination of steps which we're going to go through, right? Starting from here, the start position here, to up here, all right? So let's look at what happens as we go from sodium solid to sodium gas, right? That is step one, okay? So basically, what is happening here as you go from sodium solid to sodium gas, you're converting the solid to gas. We call that sublimation or atomization of sodium, all right? Well, I'll just stick to sublimation, because sublimation is basically the enthalpy change. Well, actually what happens when a solid is converted to a gas, right? So for delta H1, what's going on here? For delta H1, I'm sorry. For delta H1 here, that is the enthalpy of sublimation, which is going from here to here, right? Going from the sodium solid to the sodium gas. The next step is where we have the chlorine molecule being converted to chlorine atoms, right? And the enthalpy change for that is given right here, right? And we call that enthalpy of atomization, or we could call it the bond dissociation energy. And in fact, in the case of the, in this case here, because we have a half here, this would be half times the bond dissociation energy, which turns out in this case to be 122 kilojoules. So this here is enthalpy of sublimation. And then the next step is where we have the breaking of the chlorine to chlorine bond. So that would be the bond dissociation energy, but we have to put a half here because we have a half here for the chlorine. And then the next step is where we have the sodium gaseous atom being converted to the sodium gaseous ion, right? Now that would be the first ionization energy. So I'm just going to put that this is the same thing as the ionization energy for the sodium gaseous atom, all right? And then now what happens in step 4 is that the chlorine atom gains this electron to form the chloride gaseous ion. In other words, we're talking about the enthalpy change here being the electron affinity, all right? The electron affinity is the energy change that takes place when an electron gains the gaseous atom to form the corresponding anion. And then now we get to step 5. Now step 5 involves the reaction between the sodium gaseous ion and the chloride gaseous ion, all right? Now, when they combine, they're going to form the sodium chloride solid. Now, the energy required for the reverse process is called the lattice energy. So this delta H5 here would be equal to minus the lattice energy. So I'm just going to call this delta H lat. All right? That would be the lattice energy. And by definition, the lattice energy is the energy, right? Even though it says it's very negative here, but in most textbooks, they define the lattice energy as the energy required to basically convert 1 mole of an ionic compound into its constituent ions. So let me give you that definition. Let me do this here. And let me introduce a new slide. And let me take this out and this out. Okay, this thing is slowing up. I'm sorry, folks. Okay, so lattice energy, that's what we're defining here. The lattice energy is basically the energy needed to convert an ionic compound in its solid state to its constituent gaseous ions. plus X minus, gaseous ions, right? So lattice energy is delta H lat. And that's the energy needed to carry out this change, all right? So that's what the lattice energy is. And the lattice energy will be always endothermic. So delta H lattice is always greater than 0, right? So, and that's because energy is required to break up the ionic compound into its constituent ions, all right? So that's the lattice energy. So basically, going back to the Bohr-Haber cycle here, to go from here to here, that would be the lattice energy. So therefore, going from here to here would be minus the lattice energy, which in this case is minus 787 kilojoules, all right? So basically, based on Hess's law, if you remember Hess's law, it says that going from reactant to product, the enthalpy change going from a reactant to product is independent of the pathway that you take. So in this case, we can say that going from start to end directly would be equal to going from start to the first step, second step, third step, fourth step, and then the fifth step. So basically, the enthalpy change, the sum of the enthalpy changes going all the way around this direction here would be the same as this. So if we were to do the math, and I'm going to see if I can make some space here. In fact, I'm going to stop this video here, and I'm going to resume with the actual math portion of this, all right? So until next time.